Good afternoon, ladies and gentlemen. My name is Alexey Zhabin. I'm a researcher at Target Research Laboratory of groundbreaking radio communication technology of Advanced Research Foundation. Today I would like to present you the study named Simulation of Ultrashort Pulse Scattering by a Conductive Cylinder. There is a growing demand for technology capable to detect dangerous items, such as weapons or explosives, concealed under clothing or in bags. Ultra-wideband radars provide solution to detect such threats. This system exploits ultrashort pulses as a signal to study a target. The aim of the work was to estimate size of the target with a cylinder shape. For this purpose, the simulation of the ultra-short pulse scattering by a conducting cylinder was carried out. A time-domain electric field scattered by the target is divided into early time response and delayed time response. Whereas early time response depends mainly on the incident wave, the late time response contains signature of the object and can be used to estimate it. The beginning of the late time response can be estimated using the Formula 1. The late time response of a target can be decomposed into thumb of damp sinusoid oscillating at resonant frequency as shown by the equation 2. Complex amplitudes are highly dependent upon the target, but the radiating frequencies and the damping factor are independent of aspect and the form of the incident pulse. The term with the maximum amplitude was used to estimate the target size. The resonant frequency depends on the linear size of the target according to the equation 3. The electrodynamic simulation of the ultrashort pulse scattering by the perfect electrically conducting cylinder in the free space has been implemented within the finite difference time domain method using CST microwave studio software. Simulations were carried out for various target heights, while its diameter has not changed. The incident plane wave propagated from the source to the target along the x-axis with the electric strength vector along the z-axis collinearly to the axis of the symmetry of the cylinder. The scattered electric field was recorded by the probe located between the signal source and the target. The signal recorded by the probe is shown in the left picture. You can see the part of the signal associated with the incident and the reflected wave. The early time response and the late time response are well distinguishable. The late time response waveform for different cylinder heights on the large scale are shown in the right picture. The simulations were carried out for Gaussian bipolar pulses with different duration. The spectral densities of this signal are illustrated in the figure. In this analysis, the matrix pencil method was used to decompose late time response into a set of complex amplitude and resonant frequencies. The result of data processing using the matrix pencil method are presented in the table. We can conclude that the shortest pulse provide high accuracy in estimating the resonant frequency. The lower value of relative error takes place in case where the resonant frequency coincides with the pulse central frequency, where most of the signal energy is concentrated. The high value of errors for the wide pulse can be explained by the fact that the resonant frequencies correspond to the cylinder with the small heights are out of the signal bandwidths. So the bandwidth of the radiated pulse signal can be tuned by using the preliminary information about target size to increase the accuracy of estimation. If resonant frequency of target belongs to the bandwidth of the signal, the relative error decreases with the increase in the cylinder, as target with the larger radar cross-section provides more strength of the radar returns. The scattering of the incident wave with the electric field component oriented perpendicular to the cylinder axis of the symmetry was simulated. The measured signal were preceded by the matrix pencil method as was described previously. Resonant frequency calculated for all cylinder heights were in the range from 2.26 to 2.76 gigahertz, which correspond to the cylinder diameter 60 millimeters. So the size of the target was calculated using its resonant frequencies within matrix pencil methods. Waveform for the scattered ultrawideband pulse were obtained via electrodynamic simulation. The lower error in estimating the target parameter takes place if the resonant frequency coincides with the pulse central frequency, and the ultrashort pulse with the shorter duration is used as a probing signal. Therefore, the high accuracy of the target parameter estimation can be obtained within adaptive ultrawideband radar application. Thank you very much for your attention.